night, and so sorry, warnings were issued in the middle of the night. And there was a lot of uncertainty in the numerical weather prediction models, and of the 8 models that the Bureau regularly uses, 6 of them had the storm system staying off the coast, and only a couple had it coming onto the coast, which is actually what happened in the end. So we've been doing some work looking at post-processing of numerical weather prediction rainfall as a way of trying to better relate the properties that we know are important as hydrologists into improving uncertainty in forecasts from rainfall. And so here we've been using some continuous wavelet transforms as a way of trying to correct the properties of the rainfall over a range of temporal scales. Because as many of you know, it's not just the rainfall that's occurring, you know, in this current hour, but it's its relationship to the antecedent rainfall too that is going to affect how a flood plays out in reality. And so there hasn't been a lot of work done, I guess, in the use of the spectrum and wavelets as a tool to access that spectrum. And so we had some work published earlier this year in Monthly Weather Review looking at how we could use quantile mapping in the continuous wavelet transforms. So what we do is divide our time series of rainfall, forecast rainfall, up into a whole range of different spectral decompositions. And then in each one, we quantile map so that we're correcting the distribution of those. Then the cool thing is that we then use the phases or the timing of the rainfall amounts within the spectrum to create an ensemble of forecasts, because at the moment this works quite well. It uses a deterministic forecast. So then we can create an ensemble of forecasts and recombine all of these different spectrums to come up with a bias-corrected forecast, which now has uncertainty in timing as well as the amounts. And so I suggest to read the paper if you want more of the details here. I'm just kind of sticking with the big picture. But what we can see is when we applied this over New South Wales, the floods in Lismore up here in the northern rivers, we get large reductions in our root mean square error over a range of times. So we're correcting the hourly rainfall, but because we're aggregating, because we're looking at the spectrum, when we aggregate to 6 hours and 12 hours and 24 hours, we also see improvements. Sorry, at my toe, the 2 rows of figures here are for the winter rainfalls and the summer rainfalls. We also see, because the corrections allow for relationships in space, we also can improve the spatial correlation structure of the forecast. And this is really important because, you know, it's not just rainfall at a single location, but it's rainfall across the catchment that will affect the flood risk. And so when we do these phase randomizations, we can make sure that the relationship between stations is improved. And so you can see here, the red is the raw spatial correlation. So in this particular MWP model, there's too much structure. And then if we just correct the wavelet amounts, which is the blue one, then we get not much of improvement. But if we can look at the spatial structure as well, then we end up with this ensemble of realizations shown in grey, which maps our observations far better. And these are cross-validated results here. So this was, I guess, a really, you know, promising way of thinking about some really cool hydrologic tools that we've used over a whole range of other timescales, but applying them to NWP. But, you know, did rainfall really cause the floods in Lismore? And what I'd like to argue is that it's not actually just that rainfall event, but it's all of the other parts of things that are happening across the catchment that affect flood, you know, outcomes and the impacts from any particular hazard, in this case, the rainfall. So we've got, you know, our flood-causing rainfall offset with a summer of La Nina rainfalls falling on our catchment and affecting the floods. Now, those floods affect infrastructure. For example, there was big problems across the northern rivers with telecommunications systems dropping out during the floods, and therefore, you know, the state emergency service couldn't access, you know, didn't know that there were people that needed rescuing. you know, these floods are not centered within an individual event, but they're centered within a floodplain management, you know, strategy that is operated by the government as a whole. And so, you know, this is a completely different discipline from the people that are thinking about the meteorological conditions in the Bureau, where we've got consulting engineers looking at overall floodplain risk. And that part is really quite, you know, devoid of any consideration of meteorological conditions. We're just using IDF curves, annual maximum series, no thinking about why it's raining. What I'd like to argue is that when we're thinking about climate change, this disconnect between floodplain management on a risk-based basis without thinking about why it's raining is not going to serve us well, because we know that there's going to be changes in convection. We know that there's going to be changes in storm patterns, and these are all going to affect our IDF curves in ways that we haven't really accounted for yet in floodplain management. We see recommendations in Australia at the moment, in my opinion, poor recommendations of increasing rainfalls by 5% per degree of global warming, which is hugely under-conservative, given we expect 7% with Clausius Clapeyron anyway, and then we see super Clausius Clapeyron. But that's just a purely statistical scaling. It doesn't account for the changes to storm tracks or any of these kind of problems that might affect floodplain management. So we've been doing some work looking at whether we can, you know, what sort of non-stationary models for extremes might make sense to better estimate that floodplain risk. And so this is work that Leilani has been doing at the University of Melbourne with Conrad Wasco and Rory Nathan, who many of you may know from a sort of a statistical hydrology perspective, where Leilani was looking at how would we change our GEV distribution and what parameters are those, you know, which of the three parameters. And what she sort of showed was if you just change the location, which is a quite common, the location parameter, which is quite common model for changing the GEV, then you kind of get this relationship where everything just shifts up from the no change scenario. But based on our physical understanding, what climate scientists are telling us, we would expect that the most extreme rainfalls will become more extreme than the less extreme rainfalls. And so we might expect something more like this blue line or green line, where we're getting intensification of the rarest events. What Leilani showed was that when we look at a non-stationary GEV model compared to a stationary GEV model, when we're at very short durations, and so this is 6-minute rainfalls, and then we've got daily rainfalls over here, the non-stationary model is preferred, which is the improved AIC at most locations for short durations, but not so much at the longer durations where the simpler model structure is preferred by the AIC. But what Leilani also kind of looked at was the fact that when you look at the changes in the estimates of the AEP, if you don't use a GEV location and scale changing, you don't actually represent the sorts of changes in the rare events as well as the ones. So that essentially the AIC is not a good measure of the model skill, because here what we've got is the predicted changes between 1965 and 2015 in the quantile estimates in blue from the GEV model, compared to the empirical estimates fitted to the site data in grey. And you can see that if you don't have both the location and the scale changing, then we just don't have a way of representing these changes in the rarer events. And so, you know, a lot of this work has looked at AIC measures to say, well, we don't have justification for more complex model structures. But when we bring in information that we, you know, from climate scientists, then I think we get the argument that we should start to think about more complex model structures. But also what I'd like to think about is this idea that when we're designing for the floodplain, we've got structures like levees that we've already heard mentioned today as innovation in floodplain management. But they're very, you know, binary in their performance. They provide flood protection to a point, and then suddenly they don't. And the community that lives behind that levee is then not protected anymore. So this is work that Suresh, a postdoc with us and now a consultant, has been did as part of his PhD about this way of reframing the way that we think about infrastructure. And so his argument is really that we should move away from this idea that we're going to resist a flood, and then if we get something larger, particularly in the future with climate change, you know, all bets are off, to something that is more resilient, where we have a decreasing, you know, level of performance, but we don't have this drop off of failure. And so, you know, how do we design, you know, levees or floodplain management that can really think about this sort of across a range of events rather than this one design standard? Another way that I'd like to argue that we should do this is through the use of nature-based solutions, where we're essentially thinking about this idea that, you know, we're not just going to have pipes and, you know, drainage systems, but trying to modify, you know, use the strengths of the catchment with other ways to achieve a whole range of different outcomes, flood protection being one of them. And so my PhD student, Eleanor Earle, is working on this for flood risk in the Pacific, looking at how we can model this, how we can prioritise where we would put nature-based solutions across the catchment. But really importantly too, doing work with practitioners and NGOs in the Pacific about why this hasn't been implemented to date. What are the barriers? Is it data? Is it modelling? Or is it, you know, land tenure issues? Because one of the big things, you know, is that what's going to work in one location isn't necessarily going to work in another location. So last year I was in the Cook Islands, where there's quite a bit of interest in nature-based solutions. But one of the big problems that the Cook Island government has is that they don't own basically any of the land in Rarotonga. It's all owned by family groups. And so if they want to invest in infrastructure like this, it requires a whole lot of negotiations and agreement of the community in a way that would be different for a council, you know, in Australia, where they may own some land and they can invest in infrastructure like this. So what really caused the Lismore floods is that it is a really complex, you know, ecosystem of challenges that are over temporal scales and spatial scales. So, you know, for the fact that heaps of people in the community can't get flood insurance now. Why can't they get flood insurance now? Because of the 2017 floods and because of the flood history. The floodplain management has been, you know, based on our historical records of floods since colonial settlement of the Lismore area in the 1850s. But traditional knowledge of the local people suggests a range of other information about floods. And so a big flood that's led to the design of the levee in Lismore was the 1974 floods, which affected southeast Queensland and northern New South Wales, the largest flood on record until the most recent floods. But local traditional knowledge would say that that wasn't a big flood, because Aboriginal elders told of stories when if you could see the flood coming over the hill behind a specific church, that was a big flood. And apparently that didn't happen in 1974. But to date, we've had no way of incorporating those sorts of oral histories of flooding or other events into our flood design. And I think we're you know, the worse for it. But, you know, when we look at, you know, we've got all of these different climate change impacts on our climate teleconnection, that it's not just the rainfall, the meteorological conditions, but a whole lot of very specific events that led to those rainfalls. You can see here what a multidisciplinary problem providing flood, you know, resilience to this community really is. And so it's really going to take us a lot of work to talk across these disciplines and ensure that we're really, truly, you know, getting to resilient flooding. So what do I think is needed for resilience? I think we need prepared communities. We need to use the strengths of those communities. And I think that these need to be therefore very local scale solutions. And therefore we need reliable local scale information. And people need sufficient resources on the ground. We need to have, you know, a paradigm of hydrologic planning that, you know, includes non-stationary extremes, that incorporates alternative sources of information to really ensure that we've got information on climate variability. And that we're not just designing for flood standard, the one in 100-day RI, but that we're thinking about a continuum of events. I think we need to think about the ecosystem and the catchments more holistically. All of this is just thinking about water quantity, but, you know, we had major fish kill events as part of the Lismore floods, because of the really low dissolved oxygen from water quality impacts coming off the catchment. And that's really devastating to the community, to the farmers. And so, how do we start to think more holistically about the whole water cycle? And clearly we need effective climate action from governments, from a whole range of scales, as well as individuals. And we need, impact-based forecasting systems where we have uncertainty being quantified and understood and dealt with. And discussions on trade-offs between false alarms and missed events. And as already come up, this morning, continued investment in observations at a whole ranges of scales, site data, satellite data, and then modelling systems as well. So thank you. I hope, I'm really looking forward to the rest of the conference and, exploring some of these issues. If you're interested in the code associated with the wavelet transforms, you can access it from our UNSW hydrology website. Thank you.
We have time for one or two questions.
Thank you for the presentation. It gives us a lot of food for thought, I would say. But one of the things that captured my attention is the local knowledge component. We are thinking right now, lots on how, best include local and regional knowledge. So if you could share some experience from your side, some good practice, it would be very interesting.
Yeah, so I'm by no means an expert in this, and I feel like I'm actually starting the start of a journey. So I think it's about partnering with geographers and other people that have done a lot of work in this. We've been doing work with an Indigenous community in the Northern Territory, a very remote community. This is on mining impacts of water impacts on mines. And a lot of it is, particularly at least in the Australian context, is just, it's as simple as the fact that you can't just write a report and hope that people will provide feedback in the way that we might normally ask for your community consultation, as engineers call it, but that you have to sit down and you have to yarn and you have to take the time to do that. And in many of our Indigenous communities in Australia, English is definitely not the first language, but written, it's an oral culture. And so there's an awful lot of work that needs to be done in that space. I think there's a lot of work to be done with partnering with NGOs because, from the university sector, we get funding for 3 years, 5 years if we're lucky for a big project. And these relationships, they take so long and they need to be maintained. And I really think that the third sector of NGOs is actually where the biggest gains are to be made because they are there for the long term and they're delivering on those community relationships. That was one of the really interesting things about the Lismore floods was after the 2017 floods, they had a committee that kind of got together to look at local community resilience. And I saw this recently in Scotland too. Then with COVID, that community group kind of then thought about COVID resilience and helping communities respond. And so, there's a whole lot to be gained from, I guess, strong local community structures that we partner with that I think NGOs are key.